Hi, everyone. I've had a few requests to expand on and answer some questions regarding Hess's Law. Um, my personal opinion, the explanations and some of the content in this course isn't great. So hopefully this supplemental video will be helpful in explaining why and how we use Hess Law a bit. Just have to excuse some of the background noise. Hopefully it's not too loud. We've got a busy household here tonight. So first of all, what's the point of Hess's Law? This is a really great example of the what's happened to chemistry since the early 1900s. 1700s, 1800s, chemistry, totally experimental. You had to carry out experiments to figure anything out. There's nothing wrong with that. But as chemistry became more rigorous, a science with the advent of the mole concept, stoichiometry, and then also a whole bunch of other mathematical work that related to chemistry, it allowed chemists to work out what's going to happen in chemical reactions without actually carrying them out experimentally. And that's really valuable for something like a heat of reaction. This is a very useful thing to know. How much energy is going to be required or produced in a chemical reaction? But lots of reactions require specialized equipment. They might be labor and energy intensive to produce. So what Hess's law allows us to do is use a table of known heats of reaction and then figure out the energy produced or needed for any chemical reaction without actually needing to carry it out experimentally. So very valuable thing. The theory behind Hess's law and the reason why it works is that, first of all, heats of reaction sum. And then the second of all is that the heat of reaction for an overall reaction is path independent. So let's look at a visual here to see what I mean. Here's two ways to form sodium chloride. One path is a one-step reaction. Sodium ions, chloride ions combine in the gas state, releasing 411 kilojoules to produce sodium chloride. One-step reaction. That turns out to be a very difficult reaction to carry out experimentally. You have to get sodium ions in the gas state. You have to maintain chloride ions in the gas state without them combining to form molecular chlorine, Cl2. So here's actually a more realistic step of how this reaction would be carried out experimentally. You have solid sodium combining with molecular chlorine. The chlorine heats up to the gas state. You're putting in energy. Here, sodium atoms in the gas state combined with individual chlorine atoms in the gas state. You're putting in more energy, and then suddenly, as they ionize and the transfer electron happens, energy is released, and then a huge amount of energy is released. The point is, for Hess's law, if we look at the bottom, if we sum up all of these reactions, what do we find? We find that all of those individual steps sum to be equal to 411 kilojoules released. So whether you take one path or the other path, the overall net heat exchange is going to be the same. The great thing about Hess's law is that they don't have to be reactions you're actually carrying out experimentally. If you have a target reaction, which is sometimes called the overall reaction, and you want to find its heat of reaction, you can use any set of reactions as long as you can get those balanced reactions to sum to be the overall target reaction. And the reactions which can always be used and will always work are the heats of formation equations. So heats of formation are known values that have known delta H values that are found in tables. I've provided a table, and in just a second, I'm going to show you where that table is. And you can always use those for reference. So you don't have to memorize these values. They're always going to be given to you on any sort of evaluation. So What I'm going to do is go through a few examples here, and talk about some of these ideas. Before I get into this example, let me mention a few points about some of the examples in the content section, the Hess Law lesson. Some of those examples aren't very good. I think the one with ammonia, they don't properly balance the equation, expect you to do that. I don't love those examples. So hopefully by me going through an example here, this will be helpful. If you'd like some more practice questions with Hess's Law, send me an email and I can send you off a few more. So let's use this equation as an example, and let's find the heat of reaction for this equation. So I'll just put that as my unknown. My first step is always going to be balanced. However, this equation has already been balanced. My second step is to write the heat of formation equation for every substance in this reaction. So let me do that now. Okay, so I've now written the heats of formation equations here. And you might look at these and notice two things. First of all, you'll notice that I did not write a heat of formation equation for oxygen or nitrogen. The reason for that is that heats of formation are not absolute values. Heats of formation are all reference to the elements in their natural state. So the way all these heats of formation were determined is, first they said, okay, here are all the elements at 25 degrees Celsius and 100 kPa. That's the natural world, quote unquote. And then how do we form all compounds from those elements in their natural state? So the heat of formation for oxygen gas and nitrogen gas, which is their state and form at 25 degrees Celsius, is set as 0, okay? That's true for all elements. The heat of formation for all elements in their natural state at 25 degrees Celsius and 100 kPa is 0. So I can just leave them out because those values are going to be 0. Next thing you might notice here is I've got these fractional coefficients. Don't be concerned about fractional coefficients. We're not suddenly allowing there to exist half a nitrogen molecule. What you have to remember is that these coefficients just represent a ratio. And sometimes, to simplify the ratio, we want to set one value to be 1. So we want to form 1 ammonia. In order to do that, we only need 1 nitrogen atom. But since nitrogen is found as N2, we need half of that. You know, if it really bothers you, multiply everything by 2. Everything will work out the same in the end if you do it properly. Once I've written out my heat of formation equations, I'm now going to try to match up all the substances that I need in my target reaction. So let's start here. I need to get ammonia as a reactant. So here in my first reaction, I have ammonia as a product. To get it as a reaction, I'm going to need to reverse this equation. I also need 4 moles of ammonia, so I'm also going to need to multiply this by 4. My second equation here, let's see what we've got. I'm not going to worry about hydrogen because hydrogen is found in 2 equations, and it's really a pain to try to figure things out when those substances are found in 2 equations. So what I'm going to use for this equation is water. I need 6 moles of water as a product. I have 1 mole as a product. So I'm going to need to multiply this equation by 6. And you know, I didn't mention anything about nitrogen because the neat thing is, if you're only figuring out where you're going substance by substance and it's a substance that is only found in 1 equation, everything tends to work itself out. It's great. So what I'm going to do in purple underneath each equation is I'm going to do this change. Okay, so here's what equation 1 becomes. NH3, sorry, 4NH3 is a gas. Multiply it by 4 in reverse. 4 times 1/2 is 2. You see what I mean? I got 2 nitrogens as a product, which is what I need. And 3 over 2 times 4 is 6 hydrogens. Now, don't forget, you have to do the same thing to the delta H value. If the forward reaction released 45.9 kilojoules, then the reverse reaction will consume 45.9. So the sign on it's going to change because I reversed it. And then I multiplied it by 4. So since I have 4 times the number of molecules involved, don't know what happened there. Oh my goodness. Okay. Delete. Delete. Undo. There we go. Let's try that again. There's an 8, 183.6. So I reversed it. The sign changed. I multiplied by 4. 4 times the amount of heat is exchanged. Here, we multiplied by 6. And when you don't reverse it, you can kind of just add these. If you're doing this on paper, I find it's best to either write this in pencil and then you can erase things, or just to keep rewriting the equation. So 6 times 1/2. There we go. Then I need to multiply that value there, 241.8, by 6. And I'm going to get negative 1450.8 kilojoules. So what I've got in purple is what I'm interested in. So we've matched them up, and now we're going to sum these two reactions. And let me just put a line through that because we've rearranged that one. So I've got reaction 1 here and reaction 2 here. Okay, so let's see. Go substance by substance. 4NH3. Now I check to see whether it's found anywhere else. No, ammonia is only found in that one spot. So the net is 4 moles of NH3. Next up, let's go on the reactants here. 6 hydrogens. In the second equation, I have 6 hydrogens. In the first equation, I have 6 hydrogens, but as products. So there's no net change to the hydrogens. So even though they appear in the individual reactions, if you look at the overall net change, there's no change in the hydrogens, so they don't appear. Next up, 3 oxygens. And I don't see 3 oxygens anywhere else. So there's my 3 oxygens. Next, 2 nitrogens. They only appear as a product. Then 6 water molecules in the gas state. So look, when I sum the reactions, it is the same reaction as the target reaction. So here, this is where we now can apply Hess's law. If a series of reactions can be summed so that their overall net equation equals a target reaction, then we can sum their delta H values. So let me do that now. So the heat of reaction for this equation is negative 1,267.2 kilojoules. Or another way of saying this, 1,267.2 kilojoules are released in this reaction. Okay, so at this point, I've gone through an example of Hess's law. I'll remind you again, if you'd like some more practice problems, because I don't really love the ones that are in in the content there, just send me an email. I've got a ton of extra ones. So if you feel like you need some more practice, just let me know. Now, I just want to show you one other method of using Hess's law. So what we've just done, where we've written out a series of equations in this example, is called the equation method, because I'm using chemical equations. It turns out that there is a mathematical formula shortcut for this same solving the same problem. So this is called the formula method. You don't need to know this, but it is a nice shortcut to use. Okay, it looks more complicated than it actually is. What does this equation say? It says that the heat of reaction for any chemical equation is going to be equal to the sum, that's the sum symbol, the sum of the heats of formation of the products, each multiplied by their molar coefficient in the balanced chemical equation. And then you do the same thing and you subtract that of the reactants. So let's do that right now for this equation here. Okay, my first substance, ammonia. There are 4 moles of ammonia. The heat of formation for ammonia, which we calculated in, or we looked up in the previous example, is negative 45.9 kilojoules per mole. Next up, we're summing the heats of formation of the reactants. Oh, next up we have oxygen, 3 moles of oxygen. The heat of formation for oxygen is 0 kilojoules per mole. There's my shoot. And 3, 2. So let's go through this. My first product is nitrogen. There are 2 moles of nitrogen. And the heat of formation for nitrogen, oh, that's an element in its natural state, 0 kilojoules per mole. I'm summing, which means I'm adding them together. My second product is water vapor. And we have 6 moles of water vapor. And I'm multiplying that by negative 241.8 kilojoules per mole. So there is the product, right? That goes with that. Then I'm going to do this in 2 lines. Here are my reactants, 4 moles of ammonia. And the heat of reaction for ammonia, or the heat of formation for ammonia, is negative 45.79 kilojoules per mole. And then I add the next reactant, which is oxygen. There are 3 moles. And the heat of reaction for oxygen is 0 kilojoules per mole. Now, before you calculate or go any further, look at all of the operations which I've done here and match them up to the previous example. Look at what we did to the heat of formation equation for water. In the equation method, we multiplied by 6, and we're doing the same thing here. In the heat of formation equation for ammonia, we multiplied by 4, but we also reversed it. And the reversal comes in with the negative here. So 0, 0, we'll cross those out. And we'll do 6, we'll multiply 6 times negative 241.8. And then we will subtract 4 times negative 45.9. What do we get? 12, negative 1267.2 kilojoules. Just to be more correct mathematically, we'll just show that the mole quantities are canceling. So we're left with the unit in kilojoules. So this formula method here, if you use heats of formation, and it only works with heats of formation, using the heats of formation, you can get the delta H value without having to rewrite and write those equations. It's doing all of the same mathematical operations, just in a simple formula.